Good afternoon, everyone. Um, so delighted that you're all here. Today's a special day. Um, it's our part of our Pioneer series, and each part we're here to both honor and celebrate our colleague Mel Breuer. And I want to give just a quick sort of background on what this Pioneer series was intended to be about. Basically, our department has a long-standing illustrious history, but by that we mean actually it's made by people who've been here not only creating fields as they were developing their careers, but also creating the department, the school in the process. So Mel certainly is clearly part of that. Our computer engineering actually program owes a lot to Mel. And in his career, you can read his bios, it's self-evident, the number of books he's written, papers he's published, the students he's mentored, amazing number of people that are all over the world. But also he's been a pillar of our department and our school. So the Pioneer Series, our idea was to both capture part of this history, for future generations, but also in terms of a part of slice of the technical journey that they've taken, but also have a part of the oral history, the personal story that we can capture. We can't capture all that they have done, but we wanted to do that. And as a part of that, we had last semester we started this off with Bob Schultz is here again, and we kind of captured that in somewhat. We had a celebration with the department, but also there was a conversation that was recorded. Later on, we'll have a reception and we'll recount that. But today, we are really thrilled, Mel, that you're able to do this and honor us with this. So he's going to first give a talk, a technical seminar, following which our own Sandeep Gupta is going to have a conversation with Mel. It's a special thing, right? Sandeep has been mentored by Mel all these years. And so they share a long history, and so he's going to do that, and then we'll have a discussion. So that's the program. And I'm so glad that you're here. We're recording this in archive for years to come. So thank you. So welcome.
Thank you for all coming, and it's a pleasure to be here. 50 years, it's a long time. Half of you weren't even born. More than half. More than half. All right. Anyway, let me see if I can work this thing. Just a brief history. For many of you who don't know me, I got my PhD in 1965 from UC Berkeley, and I came here as an assistant professor in 1965, which was 50 years ago. I was chairman of the department twice, and I have a number of awards. Lifetime achievement, which is appropriate for someone who's senior. And another lifetime achievement award. Anyway, this is really a tutorial on computer-aided design. When I came here, computer-aided design was what's shown on the left. And so this is what I learned at UCLA and Berkeley. So computer-aided design is really, and what I mean by that is for VLSI, and it's used in computer architecture and many other places. But it's the enabler that allows us to analyze and synthesize very large systems. Okay, and what I mean by that is circuits that have over 1 billion transistors. Okay. So none of this could be done by hand correctly. And so this is what the field is. And we use algorithms, heuristics. You have to understand digital systems, and sometimes you have to understand the application area, such as signal processing. Everyone's seen this slide. Maybe a more modern update because it was, that ends at 2010. Be nice if I had one for 2015. Peter, can you get me one for 2020?
Sure.
Okay. Anyway, the point here is essentially complexity. There's the physicists and chemists at all these integrated circuit companies have been able to scale down wire length transistors to such an extent that you have over 1 million or 10 to the 6 improvement from 1970 to 2010. And very few fields have this type of growth. I always say, when I came to see, I could fly on an airplane back east at 600 miles an hour, and today I go about 700 miles an hour. Okay, so the improvement is minuscule in many industries. And how can we best handle this complexity? And it's via automation. And this just shows in microns some of the changes in wire length and transistor sizes. They're working on 14 nanometers right now. So this is a graph of, micrograph of layout, and this is an old one. The main thing to show here being the actual fabrication process, which I guess is taught and covered by electrophysics. The blue is some of the operations that go on in the design process. You have gates, you have modules, logic synthesis, we partition the circuit, we do placement, routing, verification, simulation, and generate a mask. So the end product of the CAD process are masks, which look like negatives of a photograph. They're just rectangles, mainly. The red indicates the computer-aided design field. And, for example, masks are completely automated. And simulation is an automated process. The routing and placement and partitioning are mainly automated. Things such as, I don't even have their verification is not very automated. These are open problems. Synthesis is still an open problem. But many of these areas like partitioning and placement and routing are completely automated. So over time, things we thought were impossible or too hard to automate eventually get automated. So the red moves from from right to left. Over time, things that we had automated need to get re-automated. Okay, so we have many generations of partitioning and placement and routing. Because of the scaling, electric wires don't look the same under all dimensions. Skin effects go away, resistance changes, and right now we're getting down to a couple molecules thick of copper. The whole electrical effect is different. So we have to automate because of that. And so we have developed better techniques and algorithms, and techniques change so that technology changes, okay? And so do the rules and constraints and objectives. So how do we put this all together? The fact that things are so large, that we have millions of items. We're not sorting 100 items. We sort billions of items. Okay. And the fact that most of our problems are not modeled as calculus or differential equations. Okay, but they deal with set theory, probability theory, mathematical programming, such as linear programming, algorithms like divide and conquer, and heuristics, like simulated annealing and genetic algorithms, which I don't think are taught in very many, if any, classes. So the computational complexity of these problems is usually non-polynomial in n, so they're not polynomial. And we are dealing with enormous number of objects, so hundreds of millions. So we put this all together and we find out that we actually can't solve these problems exactly, and we sometimes come up with heuristics, and that implies that we don't get optimal solutions. So a heuristic is like an algorithm that you just can't prove it terminates, or you can't prove that you get the optimal solution. So this is what the big picture of a CAD. So if you're a CAD company, you'd want to cover a CAD company for VLSI, I should say. Everything is VLSI stuff. You'd want to cover some of this material. Namely, you have to make a specification for a new, I don't know what that means. So,
Finish it. Just say no. No.
Don't say yes. I want to read it down.
Anyway, specification is the hardest to automate. And in fact, very little of it is automated. It's what the person decides that this chip is going to do. After that, we have architectural design, which is synthesis, and very little of this is automated. Logic design and design for test. This is actually synthesis, and much of this is automated. Physical design, this is once you have transistors, you have to get them on the chip. Okay, so you have to partition the circuit, do placement, actually physically place where these transistors go. You have routing, which is interconnecting all of the transistors, and mass generation. Okay. After that, you can do fabrication, and then you have testing, packaging, and more testing. And I'm in the field of the last 20 years of testing. It turns out that a large percentage of newly manufactured chips are bad. Okay, large being like 50% to 80 to 20%. And so each chip has to be tested to see if it's functionally correct, which is a very difficult thing to do. To come up with the test. It's easy to test it. It's hard to generate the test. But I'm not going to talk about that today. More partitioning. This slide is out of order. These were in the correct order this morning. So placement deals with, I have a design and I want to place them on the chip in such a way as to satisfy certain constraints and optimize certain things. The constraints could be anything from signal length to temperature, thermal, okay, things. Chips get hot, okay? And so you want to place things so that components that are going to be hot aren't too close together. Here's I can't show you a placement of a modern chip because you couldn't see anything. You'd have a billion items there. So this is a 1970 chip. IC4 is integrated circuit board with resistors, capacitors. So this is what I mean by a placement, okay? And these are it's actually, if you look at I'm not sure what color it is, gray, purple, something. But those are the interconnects on the printed circuit board. And here I picked a couple of them and made them in red so you can see them better. So as I say, all this is automatically done. So the problem is we want to find the coordinates of each component. They can be rotated, reflected, and move left and right, okay? And we would like the gates to be in a good relative position, such as here we see, well, I can't. Is this on? Yeah. Essentially, things that are going to be connected should be close together. Okay. And that's my relative position. One question is, does the placement of gates on a chip affect the number of I/O pads one needs on a chip? You can think about that. The answer is no. Does the placement of gates on a chip affect how hot a chip might get? The answer is yes. Does one need to consider circuit aspects of resistance, inductance, and capacitance in the design? And the answer in the placement, and the answer is yes, because this determines signal propagation, and signal propagation is important in going from one place to another. I'm going to skip this, okay. There's a different placement problem, which is you get FPGAs and gate arrays, and that's all the gates are already on the chip. Okay. And so this problem is an assignment problem, mainly where am I going to place gate C? Where do I place gate G? Essentially, where do I assign it? So here we can see, whoops, that was the wrong thing to do. That's the wrong thing.
Yeah.
Okay. So here I've assigned this gate G to be, I don't know, to be there.
We saw that.
Yeah, all right. And so assignment problems are well known to the field of engineering, and there are many algorithms for solving them, one of them being Munkus. We normally use Munkus. The problem in doing routing, which is, here I have output of a gate going to an input of another gate. I know that those two have to be connected. Sometimes we have multiple output fan out, and it's not clear which gates are to be connected. That's the question, is how do you find this thing? So here is what we call a star connection. Everything fans out from the gate 5, okay. Here is a daisy chain, a different way of connecting. This is what we call a Steiner tree. And this is a tour which actually has more wires than needed. You can cut any of those wires and the circuit still works. Okay. And so it's not clear which wires are going to be connected and which gates are connected to which other gates. Okay. So assume there are n unique gates. A lot of the stuff we do is combinatorics. Okay. There are n unique gates to be assigned to m locations on a chip, where m is greater than n. How many unique assignments of gates to locations exist? Okay, so how many ways can you do this? And since you choose n. Assume that Wij represents the number of wires that must go between gates I and J. Let Li be the location where gate I is assigned. Okay. So we actually know the XY coordinates of location I. Let DAB be the distance between the locations A and B. Then assume that the total wire length needed to interconnect the gates I and J is the following. Okay, so this is all straightforward math. Just the number of wires times the distance between the two gates. So the total length of the wire, assuming with the total assignment, with the, let's see, let me read it. Then the total length of wire associated with the total assignment is just given by the following. So one objective is to minimize W sub t. Okay. That would get things as close as possible, all the wire length. Okay, and that's an intuitive objective function. The problem with this formulation is that we never know how many wires go between I and J. If you have a 2-point net, then we know how many wires. If you have a multiple point net, then we don't know how it's wired up yet. So we don't know what the Wij is. So you can assume, come up with a placement and determine the Wij's, and then figure out what the Wt is, and then try another solution. Routing issues. So in routing, finding a path between two wires, let me jump ahead. Can't find. Never mind. So in interconnecting all these gates, turns out the wire is a function of line resistance and load capacitance. And so electrical engineering is required from that point of view. You can have crosstalk between adjacent wires. Okay, so a signal can be picked up on one wire because of the transition on another wire, or you can slow up a signal or speed up a signal. So again, electrical engineering. You can have overshoot and undershoot because of the inductance, and so again, the electrical engineering aspect. And in routing a clock line, you have flip-flops, and they are most systems are synchronous. Still. And there's a clock going to the flip-flops, and the clock should get to all the flip-flops at the same time. And this is difficult because of the distance. We're all at a different distance from the clock generator. So clock skew is important. And because of switching that goes on, power and ground lines, the power plane itself doesn't stay at 2.3 volts or 5 volts, whatever you want it to do. It jumps, it moves up and down. And because of that, the delay in the circuit gets modified. And so you can't, timing analysis becomes difficult. There are 4 types of chips that we normally deal with. A custom chip means you can place things anywhere you want, as long as they're not on top of each other. And then there's a standard cell where gates are placed in rows and columns. Well, no, maybe in rows. Okay. There's a gate array, where the gates are already placed on the chip, and all you have to worry about is interconnect. And there's the FPGAs, where the gates and wiring are already on the chip. And you just have to figure out a path to connect all the signals. So here's custom. Here's an example of a standard cell, where you have adders and comparators, and they're all in a row. And then you have a space between the rows for routing. And this is an example of the gate array, where the gates already exist. You just have to do an assignment of your logic to the chip, and then you route it. And then the FPGA is, you have to make an assignment, and then you route it. Here's a standard cell. I mean, a very small standard cell. You can see all the gates are on the top, and the interconnect goes underneath, and that's called a channel. And then you have more gates and more interconnect. And the channel can be made as wide as you need, so you can usually get 100% routing on this. This is the gate array, the FPGA, and it shows all the wires, the logic is there. There are programmable, oops, I can't point to this one. These are programmable switches, so you can connect wires or connect whenever you want. Two wires crossing, you can make a connection or not. These are the type of patterns you can do. The A pattern is the two lines cross, and they're on different layers. The B pattern just shows that the horizontal wire can talk to a vertical wire. Oh, I'm sorry. I was really wrong on this first one.
They're all connected.
Everything's connected there. So these are the various patterns you can have. So for this pattern, meaning the X means I have a transistor there, or I've made a connection. It looks essentially like what I have done. Essentially, no, that's not right. It's C. Essentially, W goes to line A, which is figure C. But these are the various connections you can make with FPGA. So in custom, you're interested in layout, placement, sizing, pad location, and routing. Standard cell, you only have to do, the cells are pre-assigned, pre-designed, and one needs to just place objects in rows and columns. And the channel can be made as wide as you need. Gate arrays, one needs to assign gates to fixed locations and then route the nets. And FPGA, one again needs to assign gates to fixed locations and then route the nets. But now all available routing resources are pre-defined. Synthesis is one of the latter areas to be considered. And it starts with one level of the description of something and moves it down to another level. So there are high-level languages, just like in programming, there's C, C++. There are programming languages for architecture, digital architecture, called Verilog and VHDL. And there are compilers that will compile this down to a multi-level logic, or the two-level logic. And there's a trade-off usually between the area and the delay of the logic. So logic has multi-level logic, and there's signal delay from input to output, and also the logic has area. And there's a trade-off between the area and the delay. Okay? And this is what automatic synthesis systems do for you. They give you a curve showing the various delays versus area. And when I say one level is equivalent to another level, I mean that they do the same function. verification is one of the last areas to be looked at, and is very difficult. And it's in its infancy, you might say. But essentially it says, I designed this, you designed the same thing. Are they equal? Are they equivalent or not? And this is functionally, usually rather than timing. So, and in general, this is, you can't do, all these problems are combinatorial. You can solve them all using exhaustive techniques, but because of the size of the problems, exhaustive techniques can't be used. And here's an example of two pieces of combinational logic. They each have 128 input wires. Therefore, there's 2 to the 128 unique input patterns, and no machine is going to go through that many input patterns to see if the design is right or not. Okay. So we haven't said very much about the automation of these things, but the field started in about 1950. There's one of the early applications of computers was actually the design of computers. And this slide tries to show the same information I showed earlier, but where the green is the stuff that's been automated. Okay, so partitioning has many different parts to it, but the entire thing has been essentially automated. What happened to the other projector?
You are sitting in front of it.
I'm sitting in front of it?
Yeah, it could be in your eyes.
Oh, okay.
Yeah.
Where is it?
Right at the bottom.
It's very faint.
Things in the bottom.
Well, since here, on white, on black, I see it.
Yeah.
Yeah, on the white it's
Not bright enough.
Okay. Anyway, for Boolean modeling and verification, we've developed things such as simulators, behavioral transformations, scheduling, allocations. These are the sub-problems that fall in that area, and most of these have been automated. So, test generation over here. We can automatically generate, oops. We can automatically generate tests for circuits if we have something called design for tests. So you have to be able to design a circuit a certain way, and if you do that, then automatic test generation comes into play. Anyway, so these are many of the issues that have been automated. So let me show you one of the simplest problems that we do in partitioning. Let's assume we have a graph and we want to put half of the nodes into a box X and half in Y, so that the lines, the edges that go between X and Y is as small as possible. Okay. So this is probably well known in many areas. And there are various algorithms and heuristics. Well, actually, I'm not sure about algorithms, but there are heuristics for solving this problem. One of them, anyway, let me go ahead. Here's a non-optimal solution. And here's a optimal solution. And we sometimes call this min-cut. We want to cut this graph in half, essentially put half the nodes on one side, half on the other, such that the number of interconnects is minimal. So there are heuristics for that. There aren't any good algorithms for large problems. So in PAN, we invent algorithms and heuristics that we later transform into computer programs that solve specific types of problems for arbitrary input. So a specific type might be partitioning, and arbitrary input meaning you can give it any graph you want. Okay. And we want either an algorithm or a heuristic for that. Oh, this is out of place. This shows you routing on the 4 layers of metal. And you cannot see the little red boxes every once in a while, which represents a via, meaning how you go from one layer to the next layer. And these all follow design rules. Anyway, so let me show you an algorithm. Okay, the simplest algorithm in CAD, which is I have a layer of material, and I break it up into squares. And some of the squares are occupied already by wires. And I want to find a path from A to B. Okay. And in fact, I might want to find the shortest path from A to B. And down below is shows a solution. It's not the shortest, but it's a solution. And so the simplest algorithm is called the Lee algorithm, or the Lee-Moore, or the maze running algorithm. And what it does is it says, make a model of this, a computer model, and place the integer 1 next to all the A's. Then place the integer 2 next to all the 1's, as long as the cell is blank. Okay. And then place the integer 3, etc. And you keep doing that until you get to 13, which sits on top of B. And then you just count backward, 13, 12, 11. Okay, and that will give you a minimal path. Okay, this is similar to Dijkstra's algorithm in graph theory. Does this procedure produce an optimal result? The answer is yes. Does it need to use the symbols 1, 2, 3? What about using 3? See, this used, if there are n cells between them, then it uses n like this. Anyway, and it turns out that what about only 3 symbols? And it turns out that you can use just 2 symbols, 1 and 2, to do this entire algorithm. And you can extend this to find all minimal length paths. and you can extend it to be multi-layer, and preferred directions, namely, I prefer on one layer to go left and right, and on the other layer to go in the opposite. Okay. So it's very general. Anyway. So, of course, the problem with this is that it's very slow. You can see it's n squared. And it solves the wrong problem. Namely, the problem isn't to route 2 wires, but to route all the wires. And no one said anything about you should use minimal length, though intuitively it kind of makes sense. So the next major step in routing came by recognizing that this technique, this algorithm doesn't solve our problem. And it deals with essentially what we call 2 levels of routing. Global routing and detailed routing. And they're shown here. The blocks up in this area represent large pieces of architecture like ALUs, cache, things of this sort, where you can't put a wire through it. Okay. These are called macros. And we first do placement on macros, and we end up with area between the macros, which are channels. Okay. And these channels are where we do global routing. Namely, well, essentially, I put a wire in a channel, meaning I don't know what track it's in, but it's just in that channel. Okay. And then detailed routing takes essentially all the wires in a channel and puts them into tracks. And this helps solve the problem. So there are many different routers. There's maze, which I talked about. There's line search. There's a left edge algorithm, which I'll show you. Greedy, etc. You can read all these, but these are all for special geometries. You have a special router. Okay. So routing is not just finding a path, but it's pin and I/O assignment, wire segment generation. If I have a multi-terminal net, I have to figure out which wire segments I'm going to actually put in. There's the ordering of nets. Okay, so I have all these wire segments. What order do I put them in? Because once I put in one wire, all that is blocked. That area becomes blocked. And then there's the actual layering. What layer do I put in a wire? And the routing, the actual physical path. And here's some more advanced. This just shows order. Here I want to connect A to A, B to B, C to C. And if I do A to A first, using shortest path or the Lee algorithm, then I got the top picture. Here's A to A, B to B. Okay, but if I do them in the opposite order, notice I can do it in one layer and I don't use any vias. Okay, so let me just make it clear that ordering is important. So channel routing, as I say, channel routing can be done by first making a new graph. And this new graph shows what the channels are and what channels are connected to what other channels. And then we can route, if you have some pins to connect, like these black points down there, you can route using the Lie algorithm, but over on the channel graph, not the fine graph. And essentially, so if you do that, you end up with a lot of wires in a channel. And here's, again, a picture of how this presentation was really made where I could use a pointer. I can't see. Anyway, you see you have these horizontal wires and vertical wires interconnecting things. So 1 and 4, these are terminals of the channel, the lower boundary, the upper boundary, and the net list essentially says one has to be connected to 1, 4 has to be connected to all the 4s, 5 has to be connected to all the 5s. And here's a partial solution down below that uses essentially the horizontal track as a dog leg, which means we change tracks in the middle of the run. Okay. So there's the trunks, there's the vias, and there's the branches that come up to it. And one of the problems is given a net list is to find the minimal number of tracks you need to solve this problem. Okay, so here I use 1, 2, 3, 4, 5 tracks. Okay. And the question is, can we do better? Okay. To do this, we use a horizontal constraint graph and a vertical constraint graph. Okay. And the definition is here. V of a set of nets, and E, the edges, are a horizontal constraint exists between Ni and Nj. And the horizontal constraints are defined here, if they overlap or not. And the vertical constraint graph is similar, and you have an edge. I should actually illustrate. Here you see net 1 and net, which is red, and net 2, which is green. Okay, it starts at the top and is going down below. Okay. So these have a horizontal constraint between them. Mainly, the red has to be above the green. Here, you have a vertical constraint graph, and again, 1 has to be above 3. Okay. That's what this graph shows. So the basic left edge algorithm, which turns out to be very simple, goes as follows. It ignores vertical constraints. It uses the horizontal constraint graph. dog legs are not allowed. It treats each net as an interval. Okay, there's one trunk. So you can't have this dog leg in there, for example. The intervals are sorted according to their left edge x coordinate. Intervals are rounded one by one according to this order. For net, tracks are scanned from top to bottom, and from the first track can be accommodated, and the first track that can accommodate the net is assigned to the net. Procedure, a routing solution with a minimum number of tracks. Okay. So let me illustrate this. Here I sorted the nets according to their left edge. There's no way of using my screen to... Huh?
Mouse.
The mouse. It's hard to see.
It's hard to see in the white
Right mouse on top of the right mouse.
brightness the screen that it's not making the white thing show.
Okay.
Same kind of resolution.
Anyway, if you see the light blue wires, one starts at 1 and ends at 3, and the next, okay, so it's the first, it's leftmost, okay, so it goes into track 1. The next thing you do is find the next wire that will fit into track 1. And it's going to be the one that starts in 4 and ends in 8. So it goes into track 1. And the next one is 9 to 12. Okay. No other wire fits into track 1. So you then go through the sorted list. You repeat, and the wire from 2 to 6 fits into track 2. And then the other blue fits into track 2. And this ends up giving you a minimal number of tracks, believe it or not. How many people don't believe it? All right. Send me a proof. Anyway, so this is one of the main routing algorithms. Now, this has all been enhanced so that you can consider dog legs. It's called the dog leg router. And you can consider vertical constraints. All right, finally, how much time do I have? I've run over.
It's 2:30. We should try to wrap up now, sir. Wrap up soon.
Okay. Next, I'm going to talk about placement. And this is essentially my work. Placement, always tried to minimize wire length. Okay. And this was the first work that essentially didn't look at wire length, but signals cut. So let's assume we have this layout. This is like a gate array or FPGA. And we have these artificial lines called cut lines. And essentially, if you have a placement, certain signals have to, given a placement, certain signals have to cross these lines to get from one place to another place. Okay. So if it's too hard to write. So the min-cut-based placement works as follows. It says place half of the logic to the left of one of these cut lines and half to the right, and then do a partitioning of the logic such that you minimize how many signals cross from the left to the right. And then you take one of these quadrants and you partition it in the same way. You put half the components on one side, half on the other side, and then do a partitioning process to minimize how many signals cross. And you keep doing this until essentially each of these areas has only one or two objects, in which case you have a placement. Okay. And anyway, so that's the entire story of min-cut. The question is, what is the objective function? And one objective function is to assign find an assignment that minimizes the sum of BC. C are all the cut lines. BC is how many signals are cut. So this is the total number of cuts. Okay. And this turns out to be the same as if you used a distance, wire length distance, where every net is approximated to be, the length of every net is approximate the half perimeter of the smallest enclosing rectangle. So there's nothing really new about this objective function. Another objective function would be for gate arrays, for standard cells, where essentially you have a row, two rows of logic, and you have a channel. And you place objects in L1 to Ln in such a way that you minimize how many signals you use. So this is find a placement that such that the maximum cut is minimal. And there's a third objective. This objective is the one that's used most of the time. And it's hard to read it, but the fourth objective. So they're known as quadrature, bisection, slice, bisection. And so the quadrature one is the one I showed you originally. You start with the design and you cut it in half, putting some of the elements on the left, some on the right. And then continue to do it on each of the results. There's a picture of, given an initial placement, these lines show you the wired segments that have to go in. Okay, so the output of one gate going to the input of another gate. And this is a random initial placement. This is the result after the interconnection, after placement. Okay, and this is the global routing. Okay, so again, we don't have any macros here, but essentially it puts all the wires into the channels. And this is a detailed routing, okay? So this is an FPGA, and it just shows in the red and blue some of the routing. So in summary, CAD is the enabler that allows all of these things to get done with very large circuits. And you need knowledge of technology, algorithms, heuristics, programming, architecture, and possibly an application area. Thank you. I guess questions?
Thank you, Mel. Well, there'll be a chance for questions. In fact, what we're going to do is take a short break, and we're going to have a conversation with you where people can. Sandeep will start the conversation, and we'll have people also have a chance to ask questions. But maybe should we take a
question from the presentation?
So on the presentation, if people want to ask about, Mel, some quick questions, and other conversational questions can be sort of reserved for when we start that. Any questions that you want to ask now about CAD, the journey through CAD?
Yeah, I have a question. With a gazillion connections, how do you know that any one configuration is giving you the correct answer, no less comparing 2 or 3 different ways of solving the problem?
Well, we do a lot of verification. That is, we map back from one level to the other level to see if we get the same result. So, and then we also trust the software. Peter's laughing. But essentially, we have test cases.
We have software to do the verification, but we have to trust that software.
Right. Yes.
One of the things you mentioned is we keep learning about new constraints and how we can modify our algorithms. We're in the business of automating design, and have you thought about how to automate the process of dealing with new constraints?
No.
We don't want to lose our jobs.
What's very striking is this whole, what a big data problem is. Much of what you were talking about is optimization, as you're at least laying out the routing problem, placement problem, everything, but one that is also has very complex constraints in terms of how you do it. So that's where heuristics and design insights come in.
Well, there's a hot new area called big data. Okay, this obviously falls under big data.
I mean, a couple of years ago, ISE had
Can speak louder, Sandeep.
a couple of years ago, ISE had a distinguished lecturer who was an IBM, I forget her name, who was the head of IBM research division on big data, and she presented all the 7, 8 or 9 different projects her team had done in the last few years before that. And the data sizes were significantly smaller than that you would see in a typical chip design. All of the big data, whether they're talking about the network of a wire electrical distribution network in a city, or all the water pipes in a state, all the network sizes they talked about. It was more heterogeneous in domain, but the data set size was very smaller than a typical chip on-chip design.
So that was the striking thing, to the current, big conversations going on everywhere. Like these problem sets have been dealing with. Any other questions from Mel? Students. There was in fact, probes for you that Mel had put in a slide. Now, if you read, right, there are triggers. Anyone? Don't be shy. So what? Let's take a short break. So we'll set up the